Okay, now we will start chapter 4, which is about applications of derivatives. What was the derivative? We had two interpretations, right? So the first one was derivative gives us the slope of the tangent line, right? So it helps us to find the slope, and in particular, it's helpful to find the tangent lines. The second one was interpreting derivative as a rate of change, right? With this idea, for example, we could find the speed, right? Velocity of a moving particle. And the second derivative would give us acceleration, etc., right? So now in section 4.1, we want to discuss extreme values of functions on closed intervals. So extreme values means maximum, minimum of the graph, etc. So let's get started. Learning objectives are the extreme value theorem, EVT, local relative extreme values, and then an algorithm to find extrema. Let's say that you're working on a company and you'd like to maximize your profit, right? So you can try to come up with a function that gives you the profit, and then you can ask the question, at which x values I will get a maximum, right? How can I maximize? So that's important. And similarly, let's say that you have some algorithm, you're trying to minimize your loss, right? How do you minimize your loss? So if you have a loss function, you can ask the same question. What is the minimum, right? So the definition of absolute maximum on a domain, so domain means usually an interval for us. So for a point C to be maximum, in here it means all the other points are at most f of c. And absolute minimum on the domain means at C, it means f of c is sort of minimum, right? So all the other points are greater than or equal to f of c. So maximum and minimum values are called extreme values. Absolute maxima and minima are also referred to as global maxima or minima in other books. So before even you start finding the maximum minimum, you need to ask yourself whether minimum or maximum exists, right? So let's look at a few situations for the parabola x squared. So if you look at the graph of the parabola, it's something like that, right? So it goes to infinite, right? So basically, it means, yes, this is minimum, right? So this is 0. So at x equal to 0, I get minimum. So global, I get global minimum. However, I do not have any global maximum, right? Because as x goes into minus infinite or plus infinite, the parabola blows up. So there are no maximum. Okay, so the next is, how about if I restrict myself to an interval, right? I have the same parabola, but now I restrict myself to some region like this, right? Let's say that here it's maybe 4, here it's 0, right? So if my interval is like 0, 4, here my interval was minus infinite and infinite, right? My domain, D. Here my D is this. Then we see that minimum is 0, maximum is 4, right? We have both of them. So both global max and mean exists, right? Well, we might have other situations. What could be the other situations? For example, I may have a similar situation. However, let's say that again, 4 somewhere. I leave this left endpoint of the interval open. So my D could be half open, half closed interval. So then maximum exists, right? So maximum exists, however, no minimum, right? No minimum, because 0 is not included. So within my domain, I cannot reach the minimum. Even worse can happen. I met a situation where I don't have maximum, I don't have minimum. So basically, what I can have is something like this. Here, let's say again, it's a 4. Here it's 0, but both ends are open, right? So my domain could be 0 and 4, open interval. In this case, no max and no min. So the question is, how can I guarantee the existence of maximum and minima to begin with, right? If there is no guarantee, then there is no sort of point to investigate further. That brings us to extreme value theorem. So this is extreme value theorem is related to continuous functions. If you remember, we had another important theorem, which was intermediate value theorem, IVT. And this is extreme value theorem, this is EVT. So both theorems are very important regarding continuous functions. So let's see the statement of the extreme value theorem. So it says, if my function is continuous on a closed interval, so what I mean by closed, both ends are included, right? I have square brackets. Then f attains both absolute maximum and absolute minimum. So we can guarantee with these two conditions. So I need to have continuity, and I need to have that it's continuous on a closed interval. Okay, in a closed bounded interval. Then we can guarantee the existence of both minimum and maximum. What are the situations? So one occasion is following. Let's say that I'm looking for AB, right? So my interval is A and B, right? So then what I have, so here at x2 I have the maximum, here at x1 I have the minimum. So both maximum and minimum could be inside of the interval, not at the endpoints, not on A and not on B, right? Or another situation, if you look at the second one, that extreme values might happen at the endpoints, right? Like we see the function is decreasing, so we see that the B will be minimum, A would be maximum, right? Nothing in between. So what are the other situations? Well, another situation, one endpoint may be realized as a minimum, like in here, and the maximum might occur inside the interval AB. And finally, another situation is minimum can be inside AB, and the maximum might be on the at the endpoint. So basically, what it says is, yes, I mean it might happen that minimum or maximum might be inside, but also it might occur at the endpoint. So endpoints are important, right? Endpoints are also important. We cannot sort of avoid the endpoints. Without continuity, we cannot guarantee the existence of minima or maxima, as it's illustrated in this picture. We see that at just single point, right? I'm looking for 0 and 1. So at 1, my function is not continuous, right? The value doesn't match, right? So the limit approach to 1. However, the value at 1 is 0, right? So this is not continuous, and we see that while the limit goes to 1, it never reaches 1, so the maximum doesn't exist, right? No maximum, but minimum might still be there. Okay, so basically, if you do not have a continuity, then we cannot guarantee the existence of maxima and minima. Another situation was the following, right? That we saw this parabola, right? So if you pick your domain to be something like minus infinite to infinite, so this is not like closed, right? Closed bounded interval, right? Like AB. It's not like this. So again, although the parabola is perfectly nice continuous function, it has no maxima, right? It has a minimum, but it has no maxima, for example, right? So basically, we have to be careful with the extreme value theorem. We need two conditions. So one condition is my function has to be continuous. Another condition is my domain must be closed bounded interval AB. Then I can guarantee the existence of global maximum and the minimum. Let's discuss now also extreme values, but local extreme values, also called relative extreme values. So what are they? A function f has a local maximum at C within its domain if the similar situation happens, right? All the points x are still less than or equal to f of c, but within some open interval. So within the neighborhood of the c, and the function has a local minimum if I when I sort of zoom in, right? If I look at locally around c, the f of c looks like a minimum, right? So in this occasion, we sometimes call it relative extrema. Let's illustrate with a figure. Okay, let's say that I'm interested in investigating the maximum minimum of the function given here between a and b. Well, what do we see? We see that this point D is maximum, right? It's maximum. And I see that my A is minimum. Okay, how about this C? What happens at around C? Well, what happens is if I look at this small interval around C, right, the neighborhood of C, right, if I sort of restrict myself to this picture, right, if I zoom in, right, so what I see is there is some maxima there, right, but it's not global because this particular maximum, this point is higher than this. So this is not really global maximum, but this is local. And similarly, if you look at this point E, again, if I restrict myself to this window, I see that this point f of E is minimum around here, right? All the other points nearby are bigger than or equal to E, so I see the local. Why it's local? Because the global minimum is at A, right? If you compare to this, we see that this f of A is smaller. Okay, so basically, yes, another point is here, right? This is also local minima, etc. So basically, uh, to understand better the graph of the function, uh, not only global extrema are important, but also the local extrema plays crucial role. In fact, if you know the whole picture, right? If we can find all the local minima and maxima, we sort of automatically can find global maxima and minima, right? Just looking at these local extrema. So then the question is, how do we find these maxima or minima, or how do we find local maxima and local minima? Well, uh, one option could be if you have some function on a let's say on an interval AB, what you could do is you could generate lots of sort of random points, right? Lots of points here. Let's say that you generate 1 million points, and then you compute its values, right? Let's say that you write a code, right? You compute all these values, and then whichever gives you the maximum is sort of, you can say, okay, this is my maximum, and whatever gives you minimum, you say, okay, this is my minimum, right? This is what we call exhaustive search. But it's not really exhaustive search because within interval AB, I have infinitely many points, right? But when you code it, you can only generate finitely many, even if it's million, 1 billion, it's still finite. So you might not really get, first of all, the extreme points, but you can sort of get close, right? You can get very close to max minimum. So it gives sort of idea, right? Numerically you can do it, but it's not a very good way of doing it because it's resource consuming, right? This exhaustive search, it's time consuming, etc. So if possible, we want to come up with a different way of handling this. Okay, so here's the first derivative theorem for local extrema. What it says is, if f has a local maximum and minimum at an interior point C, so C means it's interior means inside of the domain of the interval, if you like, and if this f is defined, right? So if I know that derivative exists, then the derivative must be 0. So this is how we sort of get our candidates. So we don't have to look at every single point on this interval. All we have to do is find the points where the function is 0, the derivative is 0. Why is that? So I'm not going to prove it, but let me give you an intuition. Right? Again, let's go back to this graph. So for example, I see that this particular point is local extrema, right? It's local maximum. And what can you say about this extremum? This is the peak, right? So if you look at the tangent line, if I were to sketch the tangent line, it's going to be horizontal, right? In every local minima or maxima, I see that my except for the endpoints of the interval, I see that my candidates all needs to have horizontal tangent line. What does that mean? Horizontal tangent line. Horizontal tangent. What's that mean? It means the slope is 0, right? But slope is what? Slope is the derivative, right? So at these points, if the derivative exists, it has to be 0. So that's the theorem. So an interior point of a domain of a function f where f prime is 0 or undefined, right? So it means if the derivative doesn't exist, I also need to consider it, are critical points. So these are the critical. You see, I don't have to look at all my AB interval, right? All I have to look at is the points where my function has a 0 derivative and the points where the derivative fails to exist, right? Simply because I don't know what happens there. So I have to check it. So these are critical points. So these are my sort of candidates for the extreme values. But also, I need to check the endpoints, right? Because I don't know what's happening on the endpoint. I also need to check. Because if you remember the previous examples, we get the cases when endpoints give us extrema. So here's the algorithm. So what we do is find all the critical points of f. So by critical points, we mean here, right? The points where derivative is 0 or when derivative fails to exist. Also, so I need to find all the values f at critical point and endpoints, right? So I come up with some set of values, right? And whatever the largest will give me the maximum, whatever the smallest will give me the minimum, right? It's very, very straightforward. Let's do examples. So let's say that I want to find absolute maximum and the minimum for the parabola, but you remember the parabola does not have maximum, right? However, if I restrict myself to this interval -2, 1, then by EVT it exists, right? So by extreme value theorem, both maximum and minimum exist, right? Because the parabola is continuous and I have a closed bounded interval. Here's the graph, right? So -2, here's my -2, here's my 1. So what we see? Well, from the picture it's evident that 0 is going to be my minimum, right? This is going to be my minimum, and -2 is going to be my maximum. So let's carry out the steps that we discussed in the previous slide and see whether we can really find these 2 points without looking at the graph, right? So first step is find critical points, right? Critical points. How do we find the critical points, it means I need to set f prime equal to 0. This is this is a differentiable function, so I don't have points where the derivative fails to exist. So everywhere derivative exists, so all I have to find is the f prime equal to the points where f prime equals 0. So what is f prime? Well, this is 2x, so this is 0 implies x equal to 0. So this is my critical point. This is my CP, shorthand for critical point. What is next? What is next? I need to calculate, right? So compute f of x, where x is a critical point or x is an endpoint, right? All right. Well, at critical point, this is 0, right? So at critical point, I have f of 0, which is, so my function is x squared, so this is 0 squared, so this is 0. At the endpoints, what are my endpoints? So I have -2 and 1. So at -2, if you plug in -2, it's -2 squared, this is 4. And at 1, f of 1 is equal to 1 squared, this is 1. So I came up with set 0, 1, and 4, right? So just look at these points. What is the third step? So maximum of this, so max is 4, right? And the mean is 0. Just look at the set, right? So 1 is sort of a value in between, so we just simply ignore it. We pick the minimum, which is 0. So when the minimum occurs, so this is occurs when x is equal to 4. So sorry, this is maximum. So maximum occurs when x equal to -2, and minimum occurs when x is equal to 0, right? So that sort of justifies what we see in the graph. Okay, another example. Again, we would like to find extrema for the function 10x 2 minus ln x on this interval. So on this interval, ln x is continuous, x is continuous, everything is continuous, and this is closed. So by extreme value theorem, we have the extrema, right? So there is a guarantee. Again, the first step, take the derivative. What is derivative? So by this is the product rule. Derivative of 10x is 10, 2 minus ln x, plus 10x itself times the derivative of 2 minus ln x, which is 0 minus 1 over x. So 0 minus 1 over x, which gives me 20 minus 10 ln x, and here x is cancelled, I get minus 10, right? So my f prime is 10 minus 10 ln x, and then I set this equal to 0, right? So I need to find the critical points. So if you set equal to 0, I get ln x equal to 1. What does that mean? When we get ln x equal to 1, this implies x must be the e, right? 2.7, etc. So next I need to evaluate, right? So I need to look at, I need to calculate f of 1. I need to calculate f of e squared, right? So endpoints. And I need to calculate the critical points. So at f of 1, this is 10 times 1, 2 minus ln 1 is 0, ln 1 is 0, so this is 20. Fe squared, so this is 10 times e squared, 2 minus ln e squared. But what is ln e squared? This is 2 times ln e is 1, so this is 2 minus 2 cancels out, so it becomes 0, so this is 0. And ln e is 10 times e, 2 minus ln e. Now ln e is 1, so this is simply 10 times e. But what is e? 2.7 something, so this is bigger than 20, right? So it means this point is going to be the maximum, and that point is going to be my minimum. Here's the graph, right? So here, from the graph, we see that so between 0 and e square. So e square is point where 0, right? So I'm looking for a graph here. Sorry, 1. Sorry, not 0. So 1 somewhere here. So I'm looking for the interval right here. So we see that the maximum occurs somewhere here, which is at e. So here is somewhere e. So I get maximum. and at e square I get the minimum, right? So this is 0. So the last example that we want to consider is x to the 2 over 3 on an interval minus 2 and 3. So let me look at the graph. So between minus 2 and 3, so this is the graph. So we see that at 0 I have the minimum, at 3 I have the maximum, right? But I see sort of 3 candidates, right? So one candidate is minus 2, another candidate is 3, and I have something happening at 0. So let's see what is special about 0. So remember, I need to look at f prime 0 or f prime does not exist, right? I need to look at these, investigate these points. So let's look at the derivative, f prime. What is the derivative of this? This is 2 over 3 times x to the 2 over 3 minus 1 by power rule. So this is 2 over 3 x to the minus 1 over 3. Well, this is 2 over 3 cube root of x. Well, do we have any 0? No, right? So there is no x for which this is 0. So, however, at x equal to 0, 0 doesn't exist, right? This 2 over 3 cube root of x doesn't make any sense, right? So at x equal to 0, no derivative, right? No derivative. So this is a critical point. So it means this is my critical point. So next I need to evaluate, right? I need to evaluate at minus 2 and 3 and at the critical points. Okay, so what is my f of minus 2? Well, this is minus 2 to the power 2 over 3. So this is cube root of 4. What is my f of 3? This is cube root of 9. And at 0, f of 0 is, this is simply 0. Right, clearly this is my maximum, this is my minimum. So this means x equal to 3 is the place where I get maximum, right, this place. And x equal to 0 is where I get my minimum. Okay, so I'll stop here.